Example 2. In the turbine of a gas turbine engine, the gases flow through the turbine at 17 kilograms per second, and the power developed by the turbine is 14,000 kilowatts. The specific enthalpies of the gases at inlet and outlet are 1,200 kilojoules per kilogram and 360 kilojoules per kilogram respectively, and the velocities of the gases at inlet and outlet are 60 meters per second and 150 meters per second respectively. Calculate the rate at which heat is rejected from the turbine. Find also the area of the inlet pipe given that the specific volume of the gas at inlet is 0.5 meters cubed per kilogram. Okay, so here's the question again, and I've highlighted some of the pertinent details. So we're told that the mass of the gas is 17 kilograms per second. We're told that the turbine does 14,000 kilowatts, so a kilowatt is just a joule per second. We're told that the enthalpies, so the inlet is 1,200 kilojoules per kilogram and the outlet is 360 kilojoules per kilogram. The kinetic energy at the inlet, so it's 60 meters per second. So kinetic energy, specific kinetic energy is, we're using C here for velocity, is C1 squared over 2, which is 60 squared over 2, which is 1.8 kilojoules per kilogram. And similarly for the outlet, the kinetic energy is 150 squared over 2, which is 11.25 kilojoules per kilogram. The question also tells us that the specific volume, so specific volume is volume per mass, and if I divide above and below by V, I get 1 over m over V, and mass over volume is density. So specific volume is the reciprocal of density. Okay, so we start with our steady state energy equation, and we will plug in the values. Actually, I just go back. So we're asked to calculate the rate at which heat is rejected. So we're looking for a Q value. So we're told that the work done by the turbine was 14,000 kilojoules. We're told the mass is 17. The change in enthalpy, well, it is 360 kilojoules per kilogram at the exit and 1,200 kilojoules at the entrance. And the change in kinetic energy, it's 11.25 kilojoules per kilogram at the exit and 1.8 kilojoules per kilogram at the entrance. So when I multiply that out, I get Q minus 14,000 is equal to minus 14,119. I'm going to bring the 14,000 across. So heat has been rejected at a rate of 119 kilojoules per second. Second part of the question then was to calculate the area of the inlet, and we can do that using the mass flow equation. So mass flow is equal to rho A C, where rho is the density of the air, A is the cross-sectional area, and C is the velocity. So we can rearrange that equation, that the area is then the mass flow divided by the density and the velocity. Now in our question we were told that we had a specific volume, and we're told that the specific volume was 0.5 meters cubed per kilogram. So specific volume is equal to 1 over rho. So that means rho is equal to 1 over 0.5. So I'm going to plug that in here. So instead of rho, I'm going to put in 1 over 0.5. The velocity at the entrance was 60 meters per second, and the mass flow is 17. So we have 17 divided by 1 over 0.5 times 60. and that works out to be 0.142 meters squared.